Hello, everybody. How are you all doing? We are here back learning C. We've had enough of this bingo nonsense that's been going on for the last week, and I've got Jessie on the line. Jessie, are you there?
Hi, everyone.
All right, she's there. So tonight I have a slight change. I was originally saying we're going to do hashes and sorts. We're just going to focus mostly on hashes. So sorry to mislead everybody. We're gonna do a bit mostly with like hashes. So where we are now is this is the end of sort of the C, like learning C as an additional language course. This is I call this the missing parts. So this is the stuff. These are 4 subtopics that all fit into kind of like doesn't fit into anywhere else. they're important things to really doing anything with C, but they don't conveniently slide into syntax patterns or anything else. All the basic syntax stuff, Jessie, she's mastered that. She's like expert C programmer now. So we're just not worrying about that.
We'll see.
Nathaniel, I don't feel like we missed National Scotch Day. I feel like we're just going to have a National Scotch later.
It's called a reprise.
Yeah, so that's what we're going to do. Harris, is this stand-up comedy? No, God, no. Okay. So without further ado, I'm just going to cut real fast to, let's see, what we had was this thing. And this is our... Oh, bingo, because, yeah, we're just doing bingo. So for those of you, I know 715-209 has been watching all of it, but we've been building world scale bingo. We're building this. I actually just got to the part which I thought Jessie would be interested in last night, and I called her out on the stream where I said, I hit a memory leak because that happens. I rewrote this thing to be in C because you want to scale up to the whole world, write it in C. So I wrote it in C, and I hit a memory leak, and I sort of ended the show. I was like, maybe this should be like Jessie's final exam. Like figure out this memory leak. So don't worry.
I love debugging. I'm one of those like weird freak programmers that actually prefers debugging to actual coding.
I have a feeling that after getting into Apache debugging, you're going to take that back. But
it's like exercise where you're miserable and you hate yourself while you're doing it and you question everything you thought you knew about yourself and what you like. And then when you're done, you're like, right.
That's true. That's why absolutely true. That is absolutely true. So we got this up to handling about 1 billion people. So that's fun. If you want to catch that, I'm going to be finishing that stream up later this week. So
that's really cool, actually. So
yeah, we started with a Python app. Actually, I was kind of thinking of you because, we wrote it first in Python the first day. And, we managed to get it up to like 715. What did we hit? Like around 500 RPS with the UWSGI version, which was pretty solid. So 500 requests a second, pure Python. We were done in like one session. It was beautiful. And then, somebody threw a challenge at me like, why don't you deal with like 21 million users or a couple billion? I was like, why don't we do it for the whole world? Forget 21 million. So been rewriting it in C, and then memory leaks and everything else that's fun about C. But
it's so funny that you say that, because like one of the hardest things about, well, not the hardest, but one of the difficult things for me about this pandemic and everything has been I can't volunteer with the fire department. And the lesser fun thing with the fire department is we get most of our money to fund like our new equipment and stuff through bingo for the elderly population of our community. And we've had to shut that down, and that's like our main source of income. So you say bingo and I kind of just go it's just like all of these memories of dealing, if you want a tough crowd, 75 and up.
Wow.
They throw water bottles.
They've
thrown like stuff at the bingo callers. Like they're intense.
I'm making a note because I think we're going to need to talk about that. Throwing stuff at the bingo hall. All right, so we're going to get to that as one of our topics.
Raging parties in the fire department bingo hall. No.
Okay. So yeah. Anyway, I'll finish that up this week. So where we are, we're on C. This was actually what I meant to pull up, and we have Jessie here. And so this I originally had, we're in topic 11 tonight. I'm gonna break this up. So this will be, tonight we'll just focus sort of on the first half here, which is going to be hash tables and dictionaries to somebody coming from Python. And sorting, I don't know, we'll see. It'll be kind of the reach goal for today. We'll see if we get there. Otherwise, this other stuff in the last session, I think randomness and mmap pretty much deserve their own topic. So we might break those into separate sessions. But anyway, good to see everybody, and let's get coding. So enough of this bingo nonsense. We
see my screen. All right, that helps.
All right, so I'm gonna go get the glove of drawing, and we are going to talk about hashing. So I'm gonna just cut over to the whiteboard, or if Nightshade Dude was here, the blackboard, because it's not actually white. All right, so what are we doing? Hashing and sorts. This is going to be like sort of a dotted line around that, so we'll worry about that later. And so hashes. What is a hash? Let's throw a big question mark on that. This is a topic that now again, I'm not trying to get too far into like the pure CS realm. So there's a whole art to hashing. It's almost more art than science, but there is some solid science behind it. This is one of the ways. I'm going to go and make a very argumentative statement here. So prepare your tomatoes, prepare your eggs. Just get ready to start throwing stuff.
I'm prepared.
One of the primary functions of a computer is to find stuff. And once you've found stuff, sort of like do something with it. So, and by that, I'm really specifically referring to some kind of transformation. So most of what the computer is doing is either finding stuff or doing something to that stuff. And that pretty much sums up everything that a computer does. This is more on the computational side, so you're doing some sort of, math to it. And this is more on the ordering and finding side. And having just watched Hidden Figures and remembering that, which was very fun if you haven't seen it.
I really want to see that. That's on my to-watch list.
I recommend it. I think it's very interesting because back in the day, a computer was a person.
A person,
right?
Yeah.
It was
woman, usually.
Well, this actually going back, it could be anybody. I mean, it was just somebody who was amazingly fast with arithmetic. In the period of Hidden Figures, yes, usually a woman. But that's interesting because that draws attention to this second function, because this is where we picked up the machine and we use the word computer. But I want to get into this because you're a linguist. And I think it's funny that in Spanish, they chose not to do that. They went with the other primary function of a computer, or what we would call a computer, and they basically call it an orderer. So the word in Spanish is ordenador.
Same in French, it's l'ordinateur.
Yeah, which is kind of fun. So that's someone who basically orders. These are your two primary functions of computers. Now, we've been doing a lot on the something stuff. So we've been doing transformations, we've been ripping through lists, we've been doing all the stuff that you do in C, parsing and whatnot. But we have done very little on the finding stuff. So dealing with large sets of data, dealing with things that we need to go looking up, retrieval, sort of putting order to things.
So one thing really quick is I find this very interesting from a linguistics point of view, is that the etymology of computer actually comes from Latin putare, which is to think. Mm-hmm. And so when you kind of harken back to sort of like cogito ergo sum, mm-hmm. It's a very similar idea of like I am. It's also used for the word, or it's depending on context can be used for the verb to count as well.
Yep.
Which I find really interesting because I'm doing some hand wavy stuff here because cogito
I
is
am
more
too.
About individual thinking, whereas like computare in Latin is more about like collect, like thinking together. Uh-huh. So calculating literally, which is what you're getting at. But I still kind of like, even if it's a bit hand wavy, the connection between Descartes kind of saying, I think therefore I am, and putare being to think and being the root of the computer, because I find that compute is I compute therefore I am, which is like a very cool like gets into some very futuristic sci-fi leaning conclusions, but I find it to be a very interesting linguistic connection.
Actually, Cantonese uses electric brain to your thinking point.
Really?
So,
okay, add this to our list.
All right, I'll put that on the list. Let's we'll get back to our business, but let's throw that on the list. We'll say electric brain and computer etymology. But importantly, I do want to get off the doing something transformation stuff, and I want to talk about finding. And that's mostly where we're going to be dealing with hashes. So these two topics, I had them put together, hashes and sorts, because they're really all about finding stuff and finding it quickly. So, why are we usually sorting things? We usually are just ordering it so that we can, pull something out relatively fast. Sometimes just for neatness but typically it's for retrieval. We're organizing it so that it can be retrieved quickly. Hashing is related to that. Now, they're related in the sense that they're both in the general space of finding stuff, but they don't work the same way. In the case of a sort, I'm sort of taking everything and putting it into order. And then
a certain given order, right?
Yeah, some sort of collation order.
Some kind of previously decided upon order.
Yeah, that's formally called collation. So not worried about the terminology, but there's some sort of sorting strategy. So it could be alphabetical, it could be numerical, it could be biggest to smallest, smallest to biggest, whatever the collation is. Hashing is about trying to make the retrieval instant quickly based on sort of a numerical recipe. So this is kind of like shifting more onto the function side. So whereas this is sorting is kind of more on the ordering side. So let's put everything to order. But on the function side, we want to find a way to kind of quickly pull that information up. Okay, so Nathaniel, to your question, we're not going to get into data structures too much in the C course. I was thinking about doing it as maybe the next course, but so
yes, please.
we can go deep onto data structure. So for this segment on C, I'm really just going to go very light on hash and sort, and then basically just hand wave that there's a massive field behind both of these, and we can do that in detail if we want. But for now, let's talk about hashes. So the most common case that I want to kind of pick at for a hash is you have a large list of stuff, and it's typically organized as some sort of key value relation. So, and these don't need to be the same data type. So the key could be like some sort of number, like they could be ascending, 1, 2, 3, 4. It could be a name. So here's Jesse, here's Guy, here's Nathaniel. It could be, we don't know what space the key is going to be in, but we do know that we want to be able to retrieve a particular record, like say we want to look up Guy, and actually even better is chonk. Let's have the chonk entry, right? So let's say that we want to go pull like chonk out of the library, and then we want to get sort of the corresponding value. So let's assume that these are all organized nicely. So if I find chonk, I want the stuff that's in here, and I'm being very loose about what the key and what the value are because it really depends on whatever your application is. So in the case of like a planet, it could be something like Mercury and the orbital period. So we want to have some sort of fast retrieval for the orbital period. So it's 88 something. I can't really remember.
Yeah, I don't remember exactly.
But anyway, so we have some sort of relationship between a key and a value. And how do we actually pull Mercury up? Well, one way to do it is we could actually just look through every single entry. And this is kind of the way we did it, I think, in one of the earlier courses. We just said, all right, start at the top of the list. Is this Mercury? No. Is this Mercury? No. Is this Mercury? No. Is this Mercury? No. No, 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 no. Yes. Okay, then it's here. How long does that take? Well, it depends how big your list is, right? Fair enough?
Yes.
Yeah, so if
I was writing down what you're saying.
Yeah, I mean, if my list is really big, so if we're dealing with like a list the size of like the number of planets, no big deal. I mean, we can rip through 9 entries very fast on a computer, so we don't need to be clever about it. But if we're doing something like, Social Security numbers, for example, then this might be a very large list, right? This might be like on the order of 300 million, and looking through them, not all of them are valid, right? Because there's people who've passed on. There's numbers that have been reassigned for identity theft, whatever it might be. Like this is going to take quite a lot of time if I have to go through 300 million entries just to find the one that I'm looking for. we don't want to do that.
That makes sense.
Okay, so
Efficient searching.
So yeah, one way we can deal with that is we can put all of these into sorted order, and then we can sort of use a dictionary type approach, like, how you learn to open the dictionary. You say, oh, I'm going to open it to the A, that's going to be towards the beginning, or I'm going to open it to like F, because that'll be like, I don't know, a little bit in, but not, it'll still be sort of in the first half, or like something like Z, which I know is going to be towards the end. So sorting this could cut down the search space, but it would be even nicer if I could jump directly to the entry that I want, because I know that I'm going to be looking it up by key. So I want to organize the information in such a way that I can retrieve it very quickly by key. So
right. So you want the thing that you're searching for to be in some sort of subjective first number of entries, given how you've sorted it.
Yes.
Not necessarily at the top, but just to like improve your global searching, to have it be in like, the first 10 seconds or something of searching, probably something much faster, but just arbitrarily.
Yeah.
Okay.
Yeah. And Loafbone, sorry about that. Is that fixed? I turned it down because
I can speak up.
No, I was blasting some music over the weekend. So
anything good?
No, nothing.
Oh, I'm just saying because I've been blasting like lots of Broadway lately. And
actually, it was Hamilton.
There you go. See, so, yeah, I mean, wasn't blasting Hamilton.
But on stream, I was blasting some stuff that was I don't whatever. So anyway, cool. Loafbone says it sounds better. All right, so great. Well, how do we do that? Well, what we want to do when we're retrieving data. Normally, with something like this, it's stored in an array. So I've got an array, and say I've got like 5 entries, 0, 1, 2, 3, 4. Okay, so if I want to pull, if my key is this number, then retrieval is very, very quick, because I know, for example, if these are all fixed size, then I can do some very fast math. I can say, okay, if I want the second one, all I need to know is how big this is, one of these things. So I could say, like, if this is size, like say this is 4 bytes, then I can just multiply 4. This is 4 bytes, 0, 4, 8. Okay, and I get there by just multiplying this by however many that is. So the computer's very fast at doing something, which we studied earlier. And we pop out the number very quickly, and we're able to just read the entry. Okay, it's not so easy when this data is not numerically ordered in this fashion. It's like 0, 1, 2, 3. This is nice. There's no holes in here. There's no space between 1 and 2. There's no missing, like I don't need to worry about like where's Guy on this list, because how do we put that into a number, right? This is not.
You're interested in the index, not necessarily in the value.
Yeah. And retrieval then is super quick, right? Because when I go and I look in this array, if it's called ARR, I can just type ARR, 2, and it's going to pop that thing. This is very, very fast access. So the problem with typing in something like ARR Guy, which I might want if I'm trying to look up something about me, like say, for example, my stream key. So I'm writing Twitch. Then I might have this organized with labels like this, but I can't index into a location in memory based on this value. Unless I use a hash. And that's exactly what hashes are generally for. So hashes...
So they're labeling, like indexing.
It's indexing. It's a way of taking this label, whatever it is, and turning it into an index. So putting that slightly more formally and in this type of orange color, this would be, I want to take some sort of function over some data, some sort of key, and I want to end up with some sort of index that corresponds to something that I can use in a list. So this is, in essence, this is what a hash function does. So it's responsible for moving from here to here. And then once I have this, I can go and index it into an array and say like, okay, ARR sub index. So one way of doing this would be something like, for example, if we had, Jesse and we had Guy, and we had Chonk, and we had Nathaniel.
Nathaniel, I'm sorry, you're after Chonk.
So, one way of dealing with, and don't get into trees, Nathaniel, come on. So, one way of doing this,
those I have done, unfortunately,
would be doing like some sort of lookup table. So I could just say, all right, Jesse is 1, Guy is 2, Chonk is 3, Nathaniel is 4. So I could just find it in the lookup table, and maybe this is less. I'd still have to go looking through each entry until I find it. So this wouldn't be terribly efficient to figure out, right? Because I'd have to go look in this table to get this index to be able to look in this array. Not super cool, right? Right?
Sorry, I got distracted by chat. I'm sorry. Humor. Yes, I'm following you.
Okay. So what we want to do is we want to take this key in some sense, and we want to transform it into a number. Now, we don't really care what the number is. We do care that they're not the same. So
right,
we don't want
unique hashes.
Yeah, we want our hash to try to be unique, so that, because when both of these are the same, they sort of collide on the same index. And I could build my array so that it's really an array list. So here's the index, and then entry 0, and then, there's also entry 1, and I could make like a sub array, and then I could look through each of these and say, okay, is this one Jesse? Yeah, okay, cool. I was looking for Jesse, so that's that one. Then I can go look whatever. But that's more work, because now I have to go look this thing up, and then I have to go look through this sub list. Now, unfortunately, there's not a lot of perfect hash functions.
But quick question.
Yeah.
So you've been describing, this transformation where we have kind of like the input is a key and the output is this index.
Mm-hmm.
But the assumption, right, if I'm following you, is that index will reflect like our priority as the searcher. So like it will in some way. No.
So
because then what is really the difference between the key and the index in this case, if it doesn't change it into something that is useful for us in terms of searching? It
does. This is a location in memory. It's an index. This is a key in our key space. So this might be a string, in this case. And this index is something in a memory location. We don't care what order this is in. What we care is we have a way to turn one of these into one of those. We have some sort of function that gets us from here to there. Got it?
Don't we already have that with its memory location?
Yeah, but we don't. If I say array of Chonk, what memory location is that?
Well, don't we have ways of just printing that? Because that's what we've done before. We have very easy ways of pulling out what that memory address is, right? With like pointers and stuff.
First of all, this is not valid notation. I mean,
yes.
This requires a number. I mean, it has to be like 0 or something. It has to be 1. It has to be 2. It can't be
I see.
Chonk.
So you're looking for, if you know the value, hashes help you find an index in a way.
Yeah, not value. If I know the key, so the key here is Chonk, and I want to look something up about Chonk.
So in the more C sort of way of doing it, your key, your index is like your 0, 1, 2. Let me change how I'm describing this. That's your placement in the array.
Yes.
And so if you don't know the placement in the array, but you know the value,
Wait, value? What do you mean?
So think about like the value being, when I'm used to talking about arrays in math, like you have your position, sure, but then the thing that occupies the spot at that position, it has a value, and that's the value at that position. So like if I have this array, and array's like say array 5, array position 5.
Actually, here, let me give you a simpler example.
The value is Chonk.
Let's say that there's something that maps a shape to the number of sides. Okay, so triangle has 3. Okay, square has 4. Rectangle has 4. Pentagon has 5. Okay,
so an association between like some kind of key and some kind of
just to clear up
definition.
Like terminology. Okay. This is the key. This is the value. Yes.
Okay.
But
You're using like the Python dictionary use of key and value.
Well, Python's using the much older definition.
I mean, for my reference, that's
but
what
yes,
you're using, right?
Yes. This is key, this is value. Where's index in this?
I see. Okay.
It's nowhere, right? I mean, so that's kind of my problem is what location of memory is triangle in? What location of memory is square in, rect, pentagon? What if they're not in this order? What if it was like square, triangle? Because there's no notion of order to this, right? It's whatever order they're in, this had just better be right. So this had better be 3, this had better be 4. But what order they're in is kind of irrelevant. Right?
Yes.
I mean, all we care about is that when we look up triangle, we get 3. And when we look up square, we get 4.
Okay, so let me see if I'm understanding this right. Okay, yes, I think I'm following you.
Okay, this is talking about key and value. It's not talking about index.
I guess the reason why I'm struggling is I didn't... From what we've learned in C so far, you can't do an array of like multiple data types like that. And in fact, you can't do an array that... Okay, we've never done that.
Yes, we have. We've used structs.
When?
We use
Are those
structs.
arrays technically?
No, we can make an array of structs. That's what we did with our planet example. So we had a planet name like Mercury.
I guess I thought that was more of an array of like pointers to structs.
Yes, that's an implementation detail, but yes, I mean, we effectively had a data type that captured a name, right? So for the planet, we had a name, which was, some sort of, character thing. So it's like char 20. And we had an orbital period, which was some sort of like unsigned or whatever, integer. And that was like O period. So we had exactly what we're talking about before, right?
I see what you're saying. Okay.
We had a relation between these. The problem was we had no way to jump straight to one of these names, right? So if we put all of these into an array, like we defined it as struct planet planets, and we said there were 9 of them, then we don't have a way to jump directly to, say, Mercury. Or a way to jump directly to Jupiter.
Unless we knew the quote-unquote index.
Yeah, we would have to know the index. And so the only way we could do it back then was we would basically, one at a time, have to go through this list. And we would have to say, we'd need like some sort of for loop, for basically...
To iterate through them all.
Here, I'll just borrow math notation since...
Yeah.
because it's more compact. So for each planet, basically... find the one that matches name. Name is, the thing we're searching for. And when we find it, return the associated orbital period. So we have dealt with this sort of like, concatenated data structure. But anyway, this wasn't too bad when we were going through all of the planets because there were only 9 of them, right? So we just...
To your point, when you're dealing with like 3 million or whatever, it suddenly becomes prohibitively large.
Yes. Yeah. It's not, this is our second problem of computer science, basically. Like, computers, not in the computational sense, we have them in the ordering sense, right? Because now we need to go, now it's finding the data is significant. Before it wasn't. Like in this list, finding is like nothing. It's basically free. So... But in the case of like 300 million entries or whatever sort of big data you want to work with, finding is not free. So we have to be very careful about how we do it. And that's basically the space that hashes and sorts occupy. All right, so that's our rough intuition. Are we safe on that so far? We have our terminology straight, keys and values,
I think so.
Different from indexes. Where these things land in memory is totally irrelevant. We don't care if Jupiter is stored at this location or that location. We just care that when we find Jupiter, it has the value that Jupiter needs to have for orbital period.
Right. So it's not so much, its index is almost irrelevant, but nonetheless, we need to know it so we can find it.
Yes, it's important once I put the stuff into a particular memory order. But it's not important in the sense that we don't really care which exact location of memory it occupies. We just care that we can find Jupiter when we go searching for it. or we can find triangle when we go searching for it. Okay, so that I just wanted to clear up the terminology.
I think, yeah, I'm following you.
And Marcelo Von, thank you for the follow.
Oh.
So yeah, let's just jump back here. So let's switch gears to this sort of strange green thing. So great. Oh, this is actually kind of fun. This is a little bit radioactive. So
at least to me, it matches the color that my name is in chat. So there you go.
Oh, hey, that's funny because you're showing up as purple in my chat. So
I'm like this sort of like pea soup green.
Okay.
Lime green.
All right, yeah. That's neat. So hash, this is a way of dealing with that. So the idea being that if the data, data does not need to be organized. So I shouldn't say data. I should say keys in particular. Keys not organized. So they could be in any order.
Right.
We don't really care what order they're in. We just care that when we do the lookup, it's fast. Right.
Yes.
We want to
so
be
we
able
don't care the order. We just want to find it quickly.
Yes. We just want to be able to find it quickly. So the keys are not organized. There's usually associated values with the keys. And this is typically the point of our hash function is we typically want to get the value. Now, hashing itself refers only directly to the key. It's an operation to find where basically it wants to find the index. Find the index of a given key.
So hold on, and this is me being like a little bit of a little pedantic with respect to math. Is that like if f of key is hash, technically what you're talking about is the inverse of f fed the hash results in key. Yes. So like
no.
Okay. So which is it?
No. It's no because they're not. It doesn't have to be 1-to-1. So that your inverse doesn't hold true.
What do you mean it doesn't have to be 1-to-1?
We can have hash collisions. So we can say like
what?
Yeah. Basically,
isn't the whole point of it that it doesn't do something like that?
Well, that's what we want. The problem is in the real world, it doesn't always act perfectly.
Well,
so one of the most common patterns that you have to deal with is how to deal with this notion of hash collisions, and that's the reason why your inverse is not correct, because in order for it to have an inverse, it has to be onto and have 1-to-1, right?
Yeah.
For bijection.
For like the definition of a function.
Okay, so that we don't necessarily have that for hashing. That's the notion of a perfect hash, by the way.
Well, that sounds nice.
So if we have a perfect hash, which sometimes we do, then it is invertible in the sense that you just mentioned. But hashes by default usually aren't perfect. So
and so I'm sorry if this is super ignorant, but then what the heck is the point? Like the entire, at least from my sort of perspective of you introducing, sorry, stroking.
Yeah, he just was cracking up.
He's the perfect hash. Absolutely agree. Now I'm craving corned beef. So.
That deserves a lull.
But like it seems to me quite confusing and a bit frustrating that like you invent a thing to make sure that you have this like unique identifier for keys so you can look stuff up quickly, and yet somehow the way that it's been commonly implemented breaks the very thing that you were looking to build with it. Isn't that kind of like not point? Like,
you know what?
I'm sorry, is there something I'm missing? Do it better?
You're not missing anything. What I'm going to tell you is that you're the programmer. So you're going to be doing this. So if you want me to add the restriction that you're only allowed to implement perfect hashes, this might be a very long class today.
Well, I'm not talking to me. I'm talking to somebody who's way smarter than me.
No, this is the problem. Basically, there's a lot of spaces. Some of them just don't have perfect hashes. It's not necessarily mathematically guaranteed that a perfect hash exists. But I can tell you this, like, to your point, yes, software engineers try to do what you're saying. Like, I mean,
because I understand the cryptographic hash, and like
Also not perfect, by the way. That's
Also not perfect. But I understand why that is difficult, and like it's because you are intentionally trying to obfuscate the inverse of the cryptographic function. But in this case, an inverse shouldn't be a problem. Like, in fact, that's desirable. And so it kind of seems like on the one, it's like the whole problem with a cryptographic hash, right, is that you don't want it to be super easily reversible.
Well, all right.
But
what
with
if I
this,
told you?
shouldn't you want it to be really?
No,
Unless I don't know.
It depends on your domain, but I can
Okay.
tell you that it like all things in computer science, you're usually trading stuff. So typically this isn't 100% true, but typically the better the hash is, the more expensive it is. So, and we're going to get into that in a moment, but
Expensive from a financial or computational? Or
no,
both?
it's expensive is always, for our purposes, always going to mean either something computational or something memory wise.
Gotcha.
So
Okay.
it's either speed or memory that we're typically trading. So you sort of want to get by with like the quickest hash that works pretty well.
I see what you're saying. So it's almost like you have this balancing act
Yes.
between the memory that you use
Yes.
and the speed of the search.
Yes.
And so perhaps you could make this perfect hash,
Yeah.
but then like how do you make it not slow,
Right.
which is defeating the entire purpose
Or
of the
maybe
hash?
one programmer makes, a program that requires 5 gigs of memory and another programmer does it in 1 gig of memory. Like this is one of those places where you're trading that off. So like, do the gigs matter? Like, is there only one machine, or is it going to be running on people's machines that only have 4 gigs?
Yeah.
Well,
Are you Microsoft and you have supercomputers and all you care about is speed?
Yeah,
Or, are you like me where
Microsoft
probably
cares
what
about speed? When did that happen? Okay. All right, anyway, that's
there's
getting...
a throw some shade.
Okay, sorry.
I don't know. It was the first like
That
giant
I do
to
not
talk
think
about.
of
NVIDIA,
Microsoft.
there you go.
when I think
NVIDIA
of-
cares a lot about speed.
Yeah, actually, I would say they go far on the other side. Anyway, all right. So
Yes.
that we can get into that in the second segment. So anyway, let's talk about hashes. So what are the ways that we can?
Sorry, chat.
Okay.
I love the
Yes.
sass in chat today. Thank you, chat. You're
Yep.
wonderful.
Okay, so
Okay.
how do I design
Yes.
a hashing function that takes something like triangle and outputs something like 7? Right? Because I can use this as an index, and then I can take something like square, and I can output something like 3. Again, I don't care what these numbers are because they're indices. So I just care that they're hopefully not the same.
Right.
So that was a really bad equal sign, but that was, this is here. I'll do it. That way.
Oh, it's getting worse. Okay.
All right. So how do I actually do the mechanics of this? How do I take something like this and turn it into something like that? What sort of ideas? Like what would jump to your head?
Oh God, like you, not very advanced things. Like, I mean, I'm reminded of elementary school when we did all of those like shift ciphers and stuff.
Yeah, those work.
Nerds did, right?
Actually,
Like,
we're going to be using a variant of that. So yeah, maybe you're too smart for this class. Maybe just.
so I should warn you that my dad, he is a linguist as well, and his focus in his career largely until like the last few years was cryptography. So I grew up largely around like these ideas of like how do we take something in terms of like how do we take a given language word, so a string, and how do we convert it into something that is truncated from a memory perspective, but then also like in the case of numbers, like sortable, things like that.
Yep.
So
Yeah,
it's a very fascinating idea, but also cryptography is really cool.
That's actually hashing theory. That's not
Okay,
cryptography.
well, see, I've only heard the cryptographic hash.
Now, I'm
so.
not concerned. Today, we're not really exploring cryptographic hashes because crypto has some additional constraints that it's going to throw on the hash, which I don't want to talk about right now. But we'll get to that in a little bit. Let's.
I think, though, at least for like, given that that's what I'm more familiar with, the understanding of like converting, having this hopefully unique identifier, and converting sort of a given data packet, if you will, into something that is an identifier of sorts is kind of what we're doing here. But instead of like a file and a identifying hash, we're talking about, a key an index or a key and a hash.
Yep. Well, we want to get a key, and then we know that once we find the thing, we're going to have some sort of value that we're going to pull out. And the value, so here I'm just using sides, so this was like 3, 4, 4. And by the way, don't read what he's saying because we're going to get to that a little bit later.
It's like a very bad idea. But...
so what, well, one way we could do this, by the way.
I say this only because like we've been dealing with such small pieces of data in the C class that like there are so many things that could add up to like 16.
Oh, don't worry. I've got some big data for you tonight.
Oh boy, please tell me about that
that's not to be worried about.
Identifier data that we were doing.
No, don't worry about that. So, all right, how about this for a hash function? How about the number of letters is the hash function?
Okay.
All right, so square.
I feel like you would get a lot of hash collisions.
I might. Yes. It depends on the key space. So in this key space, this would be a 5. Right?
Sorry, what do you mean by key space?
So this key space, these keys.
Okay, so in this set of keys.
Yeah, in this set of keys. So square would be 5, rect would be 4. This is a really fast hash to compute, right? Yeah. This would be pentag would be 6. That's why I didn't write the whole word out. Triangle would. I want this to be a perfect hash for now, so I'm rigging the problem a little bit. But this would be 8. Okay. I can use these as indices, right?
For now.
I mean, so if I have an array somewhere else, right, and I define this is going to be, some sort of struct array, or I could do it as 2 different arrays. I mean, we could have a key array and a value array. That'll be up to you how you want to do that. But let's just assume for the moment that it's a struct thing, and this will be like polygons. So we're going to just call this like poly. And in there we have a name, which is, I don't know. We'll give ourselves 10 characters. And, a number of sides, which we could stop. We'll just use an integer. We won't be efficient. So, and this would be like how many sides. And if I go and use this struct for my array, I could say, we could call this our database of all of our data. And let's say that it has to be some size. The size that we're going to pick is going to correspond to with our hash function. So we want to use as much space as our hash function turns values out. So let's say that this thing, we'll just make it big for now. We'll just say that it's 100. We're not going to be dealing with any objects that large, but I'm padding the space a little bit. So, and then what I can do is I can say like, assign poly. Let's just assume we have this mystical function, which would say db, at index 8 is going to be triangle, and it has value 3. Okay, and then this assign poly is basically going to conceal our silly little hash function, which is just going to say that this thing ends up, well, actually, sorry, I already calculated the hash, which is right here. So, right, because triangle was 8 in this number of letters, right?
Okay.
So I can put all of these things into this database. And if I use the same hash function, I can look them up. So I could say like look up triangle. And all this would have to do...
These, of course, being functions that we ourselves have defined.
Oh, yeah, we're going to have to write these things.
Yeah, I was going to say, I was like...
And so lookup is basically just going to compute the hash, right? It's going to say, all right, well, triangle, I have to write this function. It's 1, 2, 3, 4, 5, 6, 7, 8. That's an 8. So pull db sub 8, and that's going to have, our record of our poly. All right. Does that make sense?
I think so, yes.
Okay. Now, this is not a particularly good hashing function. It was good over this set of keys, but the minute I get another polygon that has the same number of sides, I'm in trouble.
Then you're going to have your collision.
Yeah, I'm going to have a collision.
Yeah.
So I can write my hash function to be sort of smart about this, like by treating these as buckets, which is something Strophian mentioned. I'm not going to get into that tonight. That's it's a little bit more advanced. Let's just assume that our hash functions are all perfect and they never collide.
Okay.
As our initial simplifying assumption. Okay. So this is a naive one. Another relatively naive hashing function that we could use is we could actually treat all of these letters as numbers because we know that they're stored as ASCII values, right?
Mm-hmm. Yeah, so that's kind of the shift, or like, your
there's our
really
cipher.
basic code you learn as a kid.
Yeah. So what I can do is I can say add them all up, right? Actually, here I'll get really crazy and I'll use a sum. So I could use a simple add function and say that the value of all of these things together is the value of the hash.
So that would be interesting in a language that has more, I would say, tends towards more unique combinations of letters, whereas opposed to English, I feel like we are like, there's a reason that anagrams often work in English, but there are definitely languages where anagrams don't work as effectively. And so, sorry, that was just linguist
no, that's really interesting.
Like,
though,
I think this is a much better
you mentioned
hash function than previous.
It's definitely better than the previous one. It's gonna work. It's gonna be less collision-y.
Collision prone.
Yeah, it's gonna be less collision prone, but and that's basically kind of what we're concerned with is like when we're evaluating the different hash functions that we pick, how often do they collide? Right. That's really what we want to know is, for a given key space, which is, set of keys, like how much does this hash function collide in that key space? So in this case, we're using sort of words, in this example, it's words from, geometry, would be our key space. So it's not that big a set of words. So the odds of a collision with a reasonable hash function's, pretty small. But something like, names. I mean, some of these things you might not even be able to get around. Like, if you have two people named John, then, it's going to collide. It doesn't matter what hash function you use. Like, you're going to end up with two Johns. So you might need some other way to disambiguate your entry. So that's just an important little side note. Like, collisions are sort of a fact of life.
And potentially, so this is just like, again, please don't make me do this myself, but I could also see that if you are dealing with, data structs specifically, that you could potentially use the combination of various struct attributes in your function to kind of create a multivariable hash function. And then you probably would have a lesser likelihood of some kind of hash collision because you'd be looking at unique combinations of multiple variables.
Yeah. That sounds reasonable.
But don't make me do that.
That sounds reasonable to me.
I'll go with the very simple one, please. Can I count the number of characters?
We're gonna start with the simple one. So let's do.
I was just kind of daydreaming a little bit.
Yeah, I mean, let's start evaluating these. So for now, I'm not going to worry about looking up the related value. Suffice it to say, when we have a good hash function, looking up the related value is easy. Right. The whole point of this is to make it easy to kind of index into an array. So for now, we're just going to calculate sort of an index. And let's write that as a function. So we're going to pass it a string and say to it like, hey, I want you to return whatever the number is that's going to be this hash. And for the number, let's have it always be numeric because that's nice and easy to index into an array. Actually, this is not the right array. This is the right array. But as long as we have enough memory space for this. So let's assume for now that our hash function just needs to return a character worth. So like, a character is how big?
Are you talking memory?
Yeah.
A byte, 8 bits.
Yeah, it's 8 bits. So if I assume that my hash function has to return a char, really I'm just getting at the fact that I want an 8-bit number, which, using the new modern notation would be a uint 8 _ t. So we can actually write it this way and make last miles happy. Then let's write that hash function and let's just write our first one, which is really just going to be number of letters. And we already know that we can probably do better if we do sum of letters. So we're going to write that too. And we're going to need a small set of I'll give you a couple tests to kind of work with. We can use the planets. Actually, that's probably even easier. All right, sound good?
Yes.
All right, and then once we get through that, I'll show you a better hash function.
Okay.
All right, cool.
So, quick sort of conceptual question before we get started. And again, not sort of thinking about the scope of how I'm trying to learn it today, but sort of in that wonderful world where we are trying to make our ideal hash function.
Mm-hmm.
Doesn't in some way the type of hash function that we create depend on the sort of searching we're doing?
It depends very much on the key space, which is why I keep referring to it, because if your key space is something like zip codes,
Mm-hmm.
what do zip codes look like in the US?
The easy way is 5 numbers.
Right.
The USPS one is 5-4, I think.
Okay,
so.
yeah, I mean, the full one would be 5-4, but I mean, like your basic zip code is, 5. So if we used that as our hashing function, like say we were looking up like the name of a town based on its zip code, we could actually that is its own hashing function. That, by the way, that's called the identity hashing function. So depending on your key space, that's allowed, right? Whereas using like the sum for that might be a really bad idea. But
yeah, that would be less effective.
Yeah, I mean, because, a lot of them are probably going to sum to the same value. So you're going to get a ton of collisions in that key space. But versus like if we were just doing it like we could actually just use the identity hash, which is use the thing as the hash itself. That works a lot in numerical spaces. But for string kind of problems, which is sort of what we're worried about, like, the equivalent of like a Python dictionary is kind of what we want to implement. Then we're going to be taking text data. So let's assume like words. So let's use planets as our sort of starting point. So go ahead, code this up. Give me the function for, this is our hash number of letters.
Okay. Number of letters. All right, let me find, I closed. Here's our multipad. Okay. Ooh, things have frozen for me, so I'm going to refresh. Hold on.
Okay. I'll refresh too, just to make sure.
Yeah, I think we're good. Okay, so.
Okay, now I don't normally start you off with nothing here, so I'll give you the invocation to get you going.
Thank you.
So you can have that, and you can know that this returns 0, and I'll even, because I'm such a nice guy, I'm going to throw in stdio.h. So you can
thank you.
You can have stdio.
Right.
And because we want to make Last Miles happy, and so he doesn't yell at me, let's. I'll give you standard int too, and that gives you the types like uint at. So.
Okay.
All right, you're good to go.
Okay. So ideally, we are making a new function that returns an integer.
Let's return a character. Well, an 8-bit value. Let's use the uint8 business.
Do I need to do it like that?
Yeah, _t. Yep.
Okay.
So it'll be a small. We don't want our hash function to return too large a hash. Like the size of the index space, the size of the hash function codomain is relatively small. There's only 256 possible values you could get out of this because there's 8 bits.
So, sorry, really quick. What is the naming convention in C for functions?
Those are fighting words. So I'm gonna just say you can just have fun and. Yeah, you can camel case. We've been camel casing mostly.
So let's see. What is it gonna? We are expecting it in this case, right? So we're counting the number of characters. So we're expecting it.
You might want to mention what hash it is because you're going to implement a couple hashes. So this is the make numchar. Makes some. Oh well, we're not.
And then we have a pun.
Let's do the length. All right, you want to do the sum first? That's fine.
No, we could do length first. It's okay. Make length. What is screaming snake case?
Screaming snake
And how
case.
do I do it? Because that sounds awesome. All right,
that sounds.
Oh no!
Awesome. That would be.
Oh God, I was reading. What is it?
Snake case.
The PEP 8 or whatever it's called for Python on like naming conventions.
Well, that's for constants.
Yeah, and I'm sorry, but no, I don't care how much people want me to do that. That's awful looking.
All right.
Just
Well,
no.
let's
No. That makes me
unawesome
sad
it.
in my heart. So whatever the guide says, I'll probably do for production code, but it'll still make me sad. All right, so let's think here. So we are expecting it to take in a string, right? We want to feed it a string, but technically that's going to be an array of characters.
Yep.
Can I just say character?
Array. Yep.
I can say array.
Well, I mean, you know how to define a character array.
I mean, we can just kind of say, we're going to call it word because it's going to be a word. But I don't have to. Okay, no, we're fine. I think I'm overthinking it.
Yeah, we're starting a nice, easy hash function. Let's not go crazy up front.
I know. Rust calls for screaming snake case for constants. I think Python does too.
Yeah,
and
it's common for constants.
I'm sorry, I don't know. I don't hold to that. To me, just no. Okay. Especially in like physical sciences where you have a lot of constants, that it just makes my code sad. Okay, so let's think about this. So we're given a word, and can I use the size of operator?
What type is word here?
It's a character. No, I've got to do the pointer thing because it's a pointer to the thing in the array. All right.
Yeah. It's not a single character.
I know. Okay, so can I use size of? Or is that not okay?
No, size of is not okay.
No! Why?
Because you don't know the size.
Why did you show me this magical thing if I'm never allowed to use it?
We can use it for basic types. We can't use it when we don't know. Like, for example, you don't know if you read this line out of a file because, that's where we're going.
That screaming camel case is not a thing. No. Evan, Chad is pulling the wool over your eyes. Okay. Screaming camel case, yeah. I'm sorry. So
I think it's a thing. It's a thing now.
What is the name? Is there a proper name for that? Like emo alternating, like capital and lowercase letters that we all used in, the 90s? What is that? Please tell me. That's the thing.
I would refer to that.
You got to have the little like lowercase x, capital X, like bracketing it if you want to be
all
truly.
right. You have a function to implement.
I do. Okay. I'm focused. All right. So if I can't use
Last
size
Miles. Last Miles, just for you. We're using uint 8 here.
Hi, Dennis. All right. So then I will probably make use in this case of that null terminating type.
Yep.
So I won't do my cheaty way that I was hoping to do.
No cheaty way.
I like cheating. Okay. So let me think this through. No, that won't work. I'm going to do it this way. No. Nope. I'm going to do it my way first. I'll do it the like slow whatever way, and then we can make it pretty later.
What's the first value of I?
I'm working on it.
Okay.
Hold on. Don't look.
Not looking?
You're not allowed to look.
Not looking.
Okay, thank you. I'm doing my own thing for a second. I do things in weird order. So when this is, we're going to count there. And then, but we need to find a way of iterating. This is going to be our way of iterating. So we're going to start with 0. That makes sense. We are going to need a count, which is going to be an integer, which will also start at 0. Why is it not doing the little like in? Why is I broke some?
Let's save. I think the editor got jammed.
Okay. I'm just probably spoiled.
It should have done its thing. Okay.
There we go.
It's
Okay.
doing its
All
thing.
right. That makes me feel a little better. So, Okay. So while it's not the null byte, at the very end, we are going to and I know there's some fancy C way to do it, but we're not going to do that right now. I'm going to do it my way, and then we can make it all fancy. All right. Okay, so while it's not the null byte, that might work, actually. It could be that actually, it will check at the beginning. This might work. Ah, poop. What did I just do? That actually might work.
Okay. What are we looking at?
No.
Oh, I'm not looking. Okay.
No, you are not looking.
I was trying not to look. But you said it would work, so I had to...
I know. I would like to test it, please, before I...
Well, let's get rid of that screaming camel case. I feel that I should mention this exit success is kind of the modern C approach to returning the right thing.
Okay.
In this case, it means 0. I'm referring to... there's an old Unix joke about, why did the Roman Empire fall?
Okay.
Well,
why did
lacking the number 0, they had no way to return success. So. But okay. So. I like to return 0 for that reason. Here you're allowed to cheat because you're defining it, so that's okay.
Ha! Okay. Hey, you're not supposed to be watching.
I'm not watching. I just I detected an off by 1 error. There's sort of like a spidey sense that kicks in, and that.
Oh yeah, good call. I would have caught it. You gotta give me a chance to make mistakes and learn from them.
No flexing on collapsed dynasties. Nice trophy.
I'm trying to ignore chat too in case they like.
Yeah. No, ignore chat. They're going to tell you answers. I have to look.
So I'm gonna. Oopsies! What the hell am I doing? The heck am I doing? Oh, oops, I clicked the wrong button. Okay, I expected it. Let's see. You should declare and find an identifier. Ooh, I spelled it wrong. That would also...
Look at this modern compiler telling you spelled it wrong. That's
okay.
So beautiful.
I'm ready for you to look now.
Okay, I'm not going to look. I'm going to test it.
Okay.
Ho.
Like a boss.
All right.
Ha! So there.
Looks pretty good.
Like something like, high schooler could do, but that's fine.
Hey, you got to start somewhere. Now, again, our core problem is, if we had something, it's easy to get a collision with this function. I mean, there's a lot of words that are the same length, so this would be an easily collidable function. But like I told you, we're not worrying about collisions for the moment. Okay, I'll rig the key space so that we don't get collisions.
Okay, for now.
For now, we'll get messier later. Okay, so that's your make len hash. Now let's do our make sum hash.
Okay.
Make sum.
And in this case,
your little pun there.
Haha.
Make some hash. Right. Yeah. Make some hash. All right, wait. I'm not too picky about your casing, but you do have to be consistent. So.
Oh, sorry. I was just typing quickly. Okay. So I think we're going to start in a very similar way.
Okay, there's one thing I'm going to nitpick in
Yes.
your last program before you go on. We're not going to calculate this with an int because we're returning a uint8. So this
Should I have it just match?
Yeah, this should be a uint8. So that's fine. Your program will still work fine.
Okay.
I fixed it last, Miles. I got it before you did.
Okay.
Oh, I didn't get all of it, but that's okay. Retval. This this should be uint8 too. Okay.
All right. So, oopsies. So let's see here. All right. So I think what I'm going to have to do is I'm going to need a couple of things. We're going to need is that a function? Am I good? Just, yeah, okay, that should be fine. And, oops, no, I need to be all fancy.
Mm-hmm.
And then, oopsies, you at 9.
New numbering.
All right. All right. Okay. Maybe I can be a little fancy.
Uh-oh.
Let's see if I can be a little
fancy.
fancy.
Gets us in trouble.
Oh no. Okay. All right. Maybe no. All right. I like doing things on okay, we'll see. I'll probably get in trouble for this. All right.
Well, I've always got that final exam Apache module if you want it. So.
Let's see if I can remember how to do this.
You don't need to cast.
I want to.
Okay. Well, then cast the right type if you're going to cast.
Do I have to? Okay. All right. All right. Let's see. Ooh, lordy, why is it all the way over there? Stop that. No, thank you. No! Enough of that business. I think it needs to be here. Oh, Christ. So you said I don't need to cast. Oopsies,
No, it's fine. Casting's fine. I mean, it was a care, so it's good to cast. The main reason here you don't need to cast is because care actually is a uint8. So
okay,
But you're being totally correct. I mean, like, this is
okay.
Very clear what you're doing.
Okay. Okay, so I broke it. So let's see. That's fine.
Broke it? I don't see an error.
No, I didn't get an output.
Oh, that's because I just cleared it.
Oh, stop clearing it.
Sorry.
Hold on. Let me save and refresh because I think it's.
Oh, okay. Yeah, I'll do that too. So did you hit save?
I did hit save, okay. So we should be good.
All right.
Are you having a value pop out? Because for me, nothing's
No, I haven't run anything. Here. Oh.
That's what I meant is I broke it.
Oh, you might have really broke it.
I think I really broke it. All right. Yes. Okay. So let's figure this out. How did I really break it? Okay. So
that's a good question.
Let me go through this. All right.
Here, I'm gonna freeze your output for a second. Don't touch the editor for 1 second, okay?
My hands are off it.
Okay, I'm gonna reset that and restart that. And
I wonder if part of the problem here, if I can just make a possibility, is that let me try something else real quick. Let me try. Hold on. No, that didn't even work. Okay. So the only reason what I was thinking is that
What was that?
So I was thinking that the sum of all of the oh crap, the word is ASCII numbers or whatever. Sorry, the word's escaping my head. Might be greater than
That's
255.
Okay. Overflow is totally fine.
So,
It'll just wrap around, and that's
okay.
not a problem.
So that wouldn't be causing this kind of break?
No, this is something different. Okay. I'm gonna just store your code for a second. I'm gonna reset the multi-user pad. I wonder if like some loop ran off.
Okay.
It doesn't have infinite loop detection of any sort. So I'm just gonna interrupt this, and that should throw that thing, and then we're gonna start that back up, and we're gonna start this back up, and I'm gonna delete all that. I'm gonna hit save, and let's put that back. Okay, so I'm gonna comment this thing out, and we're just gonna run it. Okay, so this is back to working. So if this thing freezes, it's because you have an infinite loop in here.
Okay.
So let's just take
the only loop we really have here is the while loop.
What are you doing to I?
Oh, I forgot to.
So yeah, you really did break multi-user pad.
I'm here to help you test it.
Oh no, that's a known broken thing. I gotta fix that.
No, that was, oops. There we go. All right,
okay.
So
let's clear this.
It should work now.
Well, actually, I commented out make some hash. So let's.
Oh, I uncommented it in random, but okay. Maybe it shows as being uncommented on my version.
Okay.
Right. You run it. Let's see what it looks like. I'll refresh.
Okay.
Let's
Cool.
save and refresh.
This good. Yep. Uh-oh. Okay.
Okay, I'm going to stop touching it for a second. Go.
Yeah. Okay, yeah, it's running on mine.
Yes. Yep, it's running on mine. Or let me try it on mine actually real quick. So let me try execute. Yes. All right, we're good. Haha.
Okay. So overflowing in hash functions, especially with like unsigned, this is totally fine. You want to wrap around your key space. But ultimately you're probably going to use a bigger key space to avoid collisions. But again, the larger you make the key space, the less chance of collision, but
you sacrifice.
Now you're throwing away a lot of memory. So that's, like I told you, you're always going to be trading, especially with something like a hash function.
Okay.
Okay, so that worked pretty well. You just knocked those two hash functions out, minus one little infinite loop that took down the editor, which that's easy to do. So, okay, so let's do slightly better.
Okay.
So by slightly better, I'm just going to show you one last hash. Do you want to? Would you rather see? I think we should just stay on hashing tonight, right? Rather than just jump ahead into like sorting. Right?
May I have a short bathroom break?
Yeah. Go right ahead.
Okay, I'll be right back.
I'll start writing.
Sounds good.
All right. So this stuff. Yeah. Let's just. Yeah, for those of you in chat, I haven't, multi-user pad is still running in a container that's like relatively unwatched. I mean, just sort of like OS systems the thing out, I think is what I implemented. It's the glaring security risk. I mentioned that in the docs, in the front page of the GitHub, which I'm sure no one looks at, but that's not what I want. We're not doing Nintendo programming tonight. So let's say, coding with some guy. And I got bingo up there, so you can check that out too. This has, I think it's just an OS system. So obviously we're going to need some job control and, some other stuff. I was thinking about going with a microkernel architecture, sort of like the micro VM style that they use for Lambda that Amazon's doing. It looked pretty heavy, So I'm trying to keep this to be relatively simple, but it's nice that they run the whole thing in like a KVM execution environment. So then you can really like police it, and it's got sort of proper runtime control. I mean, because like all your other stuff, like jails, you can break out of jails. Like where's a good place to run this stuff? I mean, ultimately this is supposed to run in the browser, so I guess I could go back to that too. This was in the it moved over here, but now we're in I want to say it's in main, but yeah, it basically just OS systems like the CaaAL, and things happen. So that, yeah. Anyway, yeah, okay, subprocess, a little better than so that's right. I got the error messages now too. All right, so anyway, you're back.
Yes.
I'm telling them the woes of why multiuserpad runs away there. That's a bug for me to fix. Or maybe you'll be able to fix it by the time we get there. All right, so I'm going to show you one more hash. Like hashing is like a pretty deep field in general.
Yes.
But you've kind of got the general idea of actually most of the popular hashes, which is, we're going to take like each character. We're going to go here. I'll just zoom in on the whiteboard. So I know Nightshade Dude's here, so I'm definitely using the word whiteboard. So we're going to take each character one at a time. We're going to do some sort of math op on sort of, the total hash value. And this is just going to kind of keep turning over as we sort of rip through our character array. And then when we're done, we're going to return the total hash value. Most hash functions look like this. Not all of them, but this, I should draw a real U there. This is sort of like the general pattern you're going to see for most hashes. And the whole part that's really kind of magical is in here. So this is the part that really gets better or worse on different sorts of hashing functions. And again, I'm still ignoring the space of like cryptographic hashes. That's sort of a different. It's related, but it's sort of a different. There's totally different requirements that you're kind of looking for. So yeah, sorry, Nightshade Dude. I gotta fix that. So anyway, the last hash that I'll show you, because there's usually the correct answer for almost all of this is I'm gonna write this big. Use a library.
Okay.
Okay. This is the right hash function. Okay. Don't generally try writing and implementing your own hash function. There's all sorts of like things like avalanche and perfect hashing, collisions, and there's like you want to be efficient on space, and you want like there's lots of different trades. You want to run it across lots of different data. Unless you really know that like some off-the-shelf hash functions aren't working for you, don't write a hash function.
Okay.
Like finding the right hash function is going to usually be messy. Don't write one. So I'm going to give that a big X. That's really important. Now, that said, if you're really living somewhere and you don't have a hash function handy, and by the way, this happens a lot in microcontrollers, you might not have like enough library space and you just need like a simple little hash to get going and whatever. One of like the great ones that's around is called the Djb hash. And I feel like we couldn't go through a class in C without talking about the Djb hash. So this is named after a dude, Bernstein, Daniel, I forget his name. It's been DJB to me for so long that I just forget. But and the Djb hash is a pretty, let's see, I can not use your length hash. It's very similar in form to what you've got. It returns, it's a 32-bit hash. So we're going to return, I've modernized it for our use tonight. So it's going to return a 32-bit number, which is sort of what DJB had in mind. And it's implemented in almost every language, by the way. So you were pretty safe, finding a version of this that's been error checked and everything else. So you're going to have some sort of string up here, and the way this hash works is pretty much the same as yours, except he juices a little bit. He starts off, your sum started off at 0.
Yes.
His sum doesn't. He likes to use prime numbers. So he dropped this, by the way, on Usenet like years ago. So it kind of famously became the Djb hash. So he sets it equal to 5381. He doesn't refer to it as sum. He calls it hash because he's not actually just going to be summing the digits. And he's going to use a character that while he's running along. And, so he's going to use a signed 32-bit character, which he's going to refer to as C. And on there, he's basically just going to say, your same kind of while every character in S, and I'm pseudocoding a little bit, then hash is going to be the old hash, which I'm just going to write it out just to be more clear. You're going to take whatever the old hash value is, you're going to multiply it by 33, and then you're going to add the character.
Okay.
And then you're going to return that. So return the hash. This is super good if you're ever in a coding interview and the interviewer, by the way, if you're ever in a coding interview, try to use the trivial or the identity hash first.
Okay.
Just be like, all right, how about I just hash by using the name? You can always use something like sum. They could say, all right, could you do better? DJB is better. So this is one. It's less important now. Like I would say, worth knowing, like if you're going into like a C interview, but reasonably you can always look it up. I will drop a link in the chat just because like hashing is a kind of important topic, and in C you don't get them. There's a nice summary of all the hashes that over the years I always end up referring to, which is here, and so you can just see. They'll walk you through different hashes and why some of them are better or worse. DJB is one of those, like, it's just simple and it just works most of the time for most key spaces. So it's a little bit better than your sum because it's got these prime numbers, and the relationship between this 5381 and the 33 is just screwy enough that the hash sort of spreads out a bit. Makes sense?
Yeah, I think so. So this list is very interesting. So I'm sorry, I'm pinning this to like probably look at in more detail later. But that's cool. Okay.
I modernized it for tonight, so I'll just include it here just so. And by the way, Theronin, I believe you're right. I think that Java does default to DJB. It's just a pretty solid hash. So here's DJB in more modern C. I left, actually, sorry, this is the not modern version. That's the version you'll find on that page. The more modern version that I modernized for your session tonight is this, which I'm just using these types, and I'm so glad that Last Mile showed up because I did this pretty much just for him. So I'm using the standard int type. So this is the nice stuff. But and again, like you saw, I threw a little bit of the performance away because these days compilers optimize. So I actually multiply by 33. He does this as a bit shift, which we did last week. So he just bit shifts this over 5, which is the same as 2 to the 5th. And then he adds hash here. So I just said, all right, well, let's just be clear so that you can see how, despite the fact that DJB is like such a good hash, it's really, really simple. Like it's just not a complicated hash. It just works really well because this 33 and these 5381 and the ASCII character set, they all just hate each other enough to sort of spread out and not collide very much on words. Whatever reason. So
it's an interesting kind of like mathematical problem.
Yeah, hashing, like you can get very deep. Like I said, we're just touching the surface, very cursory touch of hashing in general. There's different hash functions that typically apply to different sorts of domains. But anyway, that's not really a topic of C programming. I include it here mainly because you're used to having dictionary type stuff in Python, right? You know, so like if you have a database and, you know, it has like, you know, Mercury and say that's 5 and Jupyter.
I don't think so. I don't think our the multi-user pad is up for stream.
Sorry. Yeah.
In case you wanted to share your database
right.
with friends.
I'm writing that out. Say this thing is like fine. 7 and, you know, I mean, so when you're doing this kind of thing, it's converting this into a dict. This becomes a, you know, dictionary type. This implicitly has a hash function built into it. I'm not sure exactly which hash function. I think they use different hash functions depending on some of the data that comes in because, you know, it's Python and whatever. So like they're sort of building to the case of like they don't know what type of data you're going to throw at it. So there's no perfect hash function for everything. You know, there's kind of like good hash functions for certain domains. Like
that
so if
to be such a that must be such a flexible hash function because you can nest dictionaries and nest so many different data types in Python that it must be a hash function that can really handle just quite a bit of different data types. So that's impressive.
Nathaniel,
given just my baby hash function I built, I'm trying to think that through.
Yeah, I mean, Nathaniel just mentioned that it's using SIP hash, so you can actually look that up to see what they're doing. So anyway, that's about as far as we should go with hashing. Now, the only other part of hashing that we'd want to deal with is collisions and how do you deal with them, right? So what happens when we actually use this to index into an array? And that's how, I mean, just intuition wise, like how would you operate with collisions? Like assuming that some of these values might hit the same thing, you know, so for example, in our number of letters example, it's very easy for us to get a collision, right?
Yes.
So how would we deal with the fact that like two things hash to the same number? Like if we wanted to use this in an index of say like a database, right? Because when I'm building this thing, it's going to be probably some sort of struct. And, you know, I'm going to say like, I'll use my planets example. So when I had my planet thing, it was, we had a char for the name, just like 20. And then we had like, you know, a float for the orbital period. So if we build a list of planets and say we wanted to build it for a hash because we knew we were going to add exoplanets and all sorts of other stuff to it and it was going to get big, even though exoplanets would totally change your hashing function because they're usually named as like really short letter number designations. So the type of hash function you're going to use for that is very different than the kind of hash function you would use for like celestial, well, I shouldn't say celestial, like solar system type bodies.
Named bodies, yeah.
Named bodies. But let's just assume for the moment, we'll just simplify it. So we have like a hash of these, which is going to be a bunch of pointers to our database, which are actually going to go to the concrete individual records, and we'll just allocate 9. Let's allocate 1,000. And say we had this stuff all set up. Let's assume that two of these planets like collide.
Okay.
Hash-wise, I guess it'd be very bad if they collided otherwise, because, you know, if we were using the number of letters and we had Venus and we had Earth, all right, we got a collision right there. So if they both end up mapping to 5, then I can't just do a simple assignment, right? I can't say like dB of 5, right, which is really like hash of Earth, or hash of Earth.
Yeah, what would you do to handle collisions?
Is like something, and dB of hash of Venus is something. I'm going to end up overwriting the same value using this hash function we just described.
So if you have one that, so here's my thought, but I think it's wrong, is that my first thought is that you can have some kind of contingency for if the hash value already exists, right? But that kind of, when you're talking about your 3 million things, well, now you're talking about another kind of search already in there.
Yeah, that's good intuition.
So that doesn't seem right, because my first thought was, okay, well, just say that if it already exists, then you can like set the hash of Venus either to something else or use a different hash function. But all
Yeah.
of those have serious problems with them
Yeah. How would
because
you code
it's
it?
predicated on another, like a nested sort in a way.
So you are going to have to adopt a convention. You're right in your intuition. Like you're going to need
Okay.
some way to deal with collisions. Okay, so if I keep the name in the hash, I can actually look at the entry and say, was this? I don't have to trust the hash implicitly. Like
Could
I
you
don't.
do like hash Venus equals like hash Venus 1 or something so that like you're equating the hashes of like you're slightly changing the name in like a predictable fashion.
That would be one option, but now I'm messing around with the key space. So I'd
But
have to,
yeah, now you're messing with the key. Okay,
I mean,
yeah.
so that would be one way to go.
Okay.
A kind of simpler way to go is override these entries and allow them all to be arrays. So instead of defining our data structure the way we just did, we could say that each one of these database entries is actually another array. Let's say however many collisions we want to allow. So we could say that like once you get to that particular place, make sure that you've actually got the right planet. So then we might use, because before we were avoiding going through the entire list because the list might be large. Now we've sort of cut it down. Like we know that this is a 5-letter planet, so just look in the 5-letter planets bucket, and say
This is the bucketing. Okay.
this is the bucketing approach, right? So this is basically, and this could be implemented as a linked list if you want an infinite number. You could implement this as a fixed size. I'm trying to give a simpler example here. So I'm going to say that there's at most 5 entries. So what you would do, the convention we could adopt is look in DB at the hash value and then go through each of those until you find the right one. That'll still cut down our search time a lot, even though our hash function has collisions. Now, the pathological case would be all things hashed to one value. We have such an amazingly bad hashing function that and this, by the way, does happen in computer science. So like
Wait. How?
I don't want to get into how. It's just like we could have a terrible, terrible hashing function that everything hashes to the same thing.
Oh, wow.
And even if we
Okay.
made it a linked list, now we're just going to have to traverse the entire list anyway. So our hashing function saved us nothing. But this is like kind of where you get into like the how good is your hash function, like how much does it spread the data out. And that's, by the way, that like if two labels are really close to each other but you want their hash functions to be, their hash values to be far apart, that's called avalanche. Like so you could say that your hashing function has the avalanche property because it spreads things that are like so say it's like Venus and Venus, I don't know, then like
Okay.
like if those compute to almost the same number, that's not avalanche. So
Yes.
if they compute to like really different numbers, like they're wildly distributed in the index space, that would be avalanche. So you can
It reminds me a little bit, and I know it's different, but I'm just saying like some of those concepts remind me a little bit of like decision trees and entropy, and how you are looking for different ways to, when you split your data, looking at the balance of data with respect to different characteristics. So it's interesting. Hash equals 7 always.
okay. So
Oh, God.
you could have, this would be a pathological bad case of a hash function because
Oh no, Dennis, this is what's going to go down in history associated with your name.
no, Dennis would never. There's actually a funny. He may or may not consciously be doing it, but he's sort of playing off an XKCD that, like says like okay get random number, and it just always returns 4. So, like, how could you prove that that's not random? It's like might return something else. Cosmic ray could hit the computer. And anyway, so this is not really the last miles hash. So I'm not to pick on Dennis. So anyway, bucketing is one approach that you could use. Another approach is called the next, like kind of like go forward. That just pushed the.
Oh, I just wanted to copy. I'm
no,
sorry.
that's okay. I didn't realize it did that actually.
That's weird. My bad.
No, you're fine. So the next approach is basically if there is a collision, like initialize everything with sort of null, and if you hash and you try to put something in there and there's already something there, just add 1 to it.
Okay.
and just keep adding one until you get an empty spot.
Okay.
So those are the two most common strategies for dealing with hash collisions.
Hmm.
I don't think there's any point in implementing them. I think it's probably fine to pseudocode. How do you feel? I mean, would you?
I'm following you. Yeah. No, we're good.
Okay. Well, I think that pretty much wraps up hashing.